The last lesson we did was on spanning trees, minimum spanning trees, and we're going to use those today to solve some connector problems. Okay, so minimum spanning trees represent the least weight required to keep all of the vertices in a network connected, I should say. Connector problems often use minimum spanning trees to find the lowest cost to have the vertices connected. For example, if the edges of a network represented the cost to connect water to each town, a minimum spanning tree of the network would determine the lowest cost required to provide water to each town. Okay, so we're really looking at using minimum spanning trees to save money in businesses. Right, and here's the first example out of the here's the only example out of the textbook. There are 11 locations that require access to power, and these are all the vertices on the diagram. They're the 11 locations. The dashed lines on the network diagram represent possible power cable connections between the different locations. The number on the dashed line shows the minimum length of cable in meters required to connect the locations. Okay, so find the minimum length of cable needed to provide power to each location. So obviously, if you find the lowest amount of cable, then your costs are going to be as low as they can be for a project like linking all these locations up with cable. Alright, so I'm just going to choose a spot. Alright, I'm going to start here, I think. Oh no, I'm not. I'm going to start way out here where this vertex all by itself. So 60. Now from there I'm choosing the lowest again. So I went 60. From those two vertices I'm going to choose the next lowest, 40. And I keep choosing the lowest until I've got everything connected. So from 50 I can go 70 or 60. Well, or this spot here is 50, so I'm going to go there, out to there. And the last, I've still got, I've missed one. That vertex has to be added, and that vertex. So I've got all my red vertices connected. Alright, and I've done it in the lowest possible numbers or weights. Then you add up 60, 60, 40, 60, 40, 50, 50, 50, 40, 60. Add them all up and it'll tell you the minimum length is 510 meters. Okay, so that's called a minimum spanning tree. It's connecting up all of those vertices and it's telling you this is how much, or this is how much cable you need. Okay. A second example, the computers in each of the offices at Pattonville High School need to be linked by cable. The following map shows the cost of each link in hundreds of dollars. What's the minimum cost of linking the 5 offices? So A, B, C, D and E are all the offices. Doesn't matter where you start. I'm going to start at E and I'm going to choose the lowest again. Excuse me. So the smallest I saw was 5. The smallest again I see is 5. I'm going to go along this 8, but it doesn't matter which 8 I choose or I choose, and then I'm going to choose the 3. So I've linked up every vertex. I could have gone D to C and C to B. Okay, would have cost the same amount. So what's the minimum cost of linking the offices? I do need to remember this is in hundreds of dollars, so that means 600, 500, 500. Add them all up. The minimum length is 21, which represents a cost of $2,100 or $2,100. Alright, so today you're going to work through 2G and start putting your knowledge of networks to a actual, problem, a reason, or how you might actually use it. Okay? Have fun.